Good evening, Raja.
Good evening, sir.
How do you do?
Yeah, very good, very good.
Great.
How are you?
Doing good, yes.
Yes, Anushka, you can go ahead.
Yeah, Anush.
Okay. Uh, Good evening, everyone. So, my name is Sharnava Chatraj. I'm currently in the diploma level of the IIT MBS program. Okay, so I'll probably start sharing the screen. I'm not sure if you can see it, everyone. Okay, so I will be switching between the PDF and I'll be writing some stuff up. I'll like everyone to actually, stop me if I'm speaking too quickly, or if it's a very small doubt, just interrupt me and ask me at that very instant. Okay, so as it has been told, probably I've actually messaged this PDF already. So if you want, you can just open it up in some tab and follow. So the point of discussion today is logistic regression. So what is it? Well, it's a classification technique. It's a supervised learning setup. The setup is a supervised learning setup. It's a classification problem. And well, this is one way to actually solve the classification problem. The point of the talk is first we'll propose the algorithm and then, ask some questions and see if we can answer them satisfactory in some sense of satisfaction to some extent. Okay, whatever. So let me just propose the algorithm. So my xi, so I'm in a Euclidean space of a d-dimensional Euclidean space. The sample points are in RD and they have been labeled as either 0 or 1. So there is a comment at this very line. Choosing yi, the label, as 0 and 1 is not really the best way to do it. In general, we choose -1 or 1. And then what happens is the formulation becomes a little simpler. But then whatever we are discussing today will remain almost the same. If you know, in the perceptron algorithm or in the SVM setup, we use -1 and 1 as the labels instead of 0 and 1. And if you want, yeah, and then I'll propose some links later on, which you can actually see where they have actually used -1 and 1. But I'm sticking to this because in week 10 of MLT lecture, the professor actually uses this label setup. Okay, so how do we do? Well, we start by defining what we call, this is what is known as a sigmoid function. And then we say that the probability that I see some y given some sample x is of this form. Well, the probability is of this form. And then a very natural question is, why do we take this? And well, it is not enough to say. The reasons that are quite popular are that this function is between 0 and 1, so it gives you a probability density function. These are continuous, so it's probably density function. But then you can cook up multiple such functions where it is between 0 and 1. And even if it is not between 0 and 1, for example, if it is between some a and b, what you can do is you can transform the function such that the function is bounded between 0 and 1. So why, given the plethora of choices, why do we actually choose this function is quite questionable. But then by the end of the lecture, I'll try to provide you with an answer. Okay, moving forward, there is some, so I will like everyone to be familiar with this way of representing probability of y given x. This is exactly this, but written quite compactly. So if you can see, if hw of xi gives you 1, then this term actually vanishes. So like if hw of xi and you predict its label as 1, then this goes away and this is the only thing that is left. And the same happens if hw of xi predicts the label y equal to 0. Then this term actually goes away. This becomes 1 and this is the one that's remaining. And then you can actually verify I've written this very thing, but in a compact form. Why this form? It's quite debatable, but one thing that this style of function is differentiable. But then you can actually take some kind of exponents of this very function, but we don't take that, and why we don't take that is not the point of the talk. Okay. One more thing, that in place of W transpose X, we could have written W transpose X plus B, but then what we have quite cleverly done here is in place of W, we have accommodated, okay, so this is a typo, this will be B, not D. And then we have, actually shifted X from RD to RD plus 1 with a 1. And then you can see that W transpose X is this. So it's not that we are taking only W transpose X, but then W transpose X plus B is already inbuilt by how we set up the W and X's. For the sake of simplicity, we will not do this dash, we will refer it as W and Xi only. And one more thing, this is just the I on the top is just referring that it's the ith example. That's like, this is kind of popular in the literature. Okay. Before we go on, we will use the gradient of this function quite often. So like if you do the gradient with respect to W, if you take the gradient, it's like this, and you can see it's quite nice. The form is nice. Okay. So now, how do we even predict? Well, we have to like dream a little bit. So that's why there is this wishful thinking. So if we get this W, then what we can do is we can just plug in an X and then see what's the probability of Y equal to 1. And then again plug in X and see what's the probability of Y equal to 0. And then take the maximum between them. And then that's precisely how we have written it here. So Y hat denotes the prediction. So we did this prediction. So that's the argument that maximizes the probability, and Y is the variable that changes. So Y is 0 or 1, and then we just take the maximum. And how do we do that? Well, we go our maximum likelihood estimate way that you should be familiar from statistics too. Okay, but then why MLE? Well, that's a point. That's a very interesting question. Why we see MLE in so many algorithms, but then that's again not the point of the talk today. Yeah. If possible, later someday I can give some kind of presentation and show. But then two things can be said, that MLE is an unbiased estimator, and it's the best asymptotically, it's the best estimator given we have no prior information about the parameter, or actually no information about how my data is generated. So MLE is the best we can do asymptotically, of course. Okay, so what's the way? So we develop a likelihood function that just probability, that's just the product of the probabilities of the samples, and I've just replaced this function. So that's why I've actually previously mentioned this function, and that's exactly what I've done. We have all seen that it's better to and then we actually maximizes the log function, but then we see that it's better to maximize the log likelihood in place of the likelihood function. Why we can take the log? Well, log is monotonic. So if my likelihood function is increasing, the log of the likelihood will also increase. So I have not actually formulated the problem, but then what we are doing is this. What we are doing is we want our WMLE is defined as the argument that maximizes the log likelihood. Can anyone just say that this red color is visible or not on the black screen? I think I should have used.
It is visible. Yes, sir, visible.
Okay. Please just call me Swarnava. I will prefer that. Okay. So now there's a pun here that how we do it. We actually differentiate it and set it to 0. But then you can see that I've written that it's not analytically solvable. At least many clever people have tried, but they have not been able. So we go the gradient route. I have not shown why the gradient wave works, but then that's a prerequisite to the lecture, which I've also not mentioned, but okay. So what we do in general is that we set some W0, and then at each of the iterative steps, what we do is we find the gradient along which, before that we are maximizing. So please don't get confused with gradient descent. So we will do what we call as a gradient ascent, not the gradient descent. So people who already know there is not a negative sign here, is a positive sign. But then what we do is we move along the direction of the gradient, which is the direction of the steepest ascent. In the gradient descent rule, we would move opposite to the direction of the gradient. And so that's how we actually formulate the gradient ascent update rule. The eta is what we call as a learning parameter. Well, this learning has nothing to do with the learning of the algorithm, but it's still learning parameter. There are multiple ways we can actually give a static eta. We can like each update can be made quite small, and then we don't need to vary eta. But then we can also do some kind of a damped version of it. Like we can modify eta after every step. There are some good ways to do. For example, the Army-Host condition provides a good bound of how you should choose eta at each of the iteration, and interested people can check that out. Army-Host condition. You can see there is one improvement that we can do is that you can see there is a summation here. If n is too large, then this computation takes more time. So what we can do is, instead of like calculating the gradient of the entire sample data set, we can pick one of the samples and then just use that. Well, and then we can actually show that the W optima that we get from SGA converges to the W optima that we get from gradient ascent with like high probability. Okay, but we won't go to the proofs of that. Okay, but where we will go through is we'll actually prove that the log likelihood is concave. Okay, well, it's not completely concave, but then let me just finish. So okay, now you have to recall what we call when we call a function concave. You can see this in week 9 and 10 of MLF, if I'm not wrong. There we get multiple definitions of how a function is concave, but then if the function is double differentiable, which we will see it is our likelihood function, then any function which is double differentiable, we can say if it is concave if the Hessian is negative definite. So this is a notation that's quite popular. This actually shows that the Hessian precedes 0 in some order, not necessarily a strict less than, but then its equivalent formulation is this bilinear form. So this and this are equivalent, and if you can show that this is true, then you can say that f is concave. But then what we'll see that we don't really have a strict inequality here, but less than or equals. How you can actually take the gradient, I've written this explicitly before, and then what you can do is you can create the Hessian matrix. That's the second order differential in vectors, and then that's this. Okay, one thing that if you want to see how this comes, a good advice is to set n equals 2 and then try it out. Like explicitly create the matrix and then try to formulate each of the elements of the matrix, and then you will see that this makes sense. And if you are very comfortable, then you can actually see that why this is true. Okay. Here now, if you see that what is HW of xi, HW of xi is a value between 0 and 1, and then 1 minus HW of xi is also a value between 0 and 1. Then the product of them is strictly greater than equal to 0. And then what you have is now this is 0, and then V transpose HV. If you multiply a V transpose before this and a V after this, you will get this form. And again, it's a good way to actually set n equal to 2, V as a vector in R square, and then actually explicitly calculate out and then see that it matches this form. So this is what we get. Okay, so here one property that we have used is this. So if you have two matrices and then you take its transpose, then what happens is you get this. So what happens is that if you can see that V transpose x of I, and if you take a transpose, okay, sorry, not this one, but this. suppose xi, and then you know, and this is one property that is used, and the second property that is used is this. This is Euclidean norm, by the way. People who don't know don't really need to care, but then that's the usual norm that we do in ML, in maths too, right? Yeah. Okay. Now, so this is a positive quantity, so it's actually greater than equal to 0. This is greater than equal to 0, so the sum is greater than equal to 0, and then there's a negative, so it's actually less than equal to 0. So why did we even try to derive this? Well, what happens is now we know that LW is concave function, or it is linear in some directions. But then what I can say is that if it has a global maxima, then my gradient ascent rule will actually converge to the local maxima, and it will not get stuck in some kind of a, global, and it will not get stuck in some kind of a local maxima. Let me repeat, it's concave, so it's concave or linear in some directions, but if there exists a global maxima, then my gradient ascent will actually converge to that global maxima. It will not get stuck in local maxima. Okay. So that actually justifies why we are using this method. Okay, so this is one method. Well, all of this you will get partially in week 10 of MLT under perceptron algorithm in the later. So in the week of perceptron algorithm, actually the professor actually gives this algorithm, the gradient based, but then this is something new that I'm trying to propose today. So what we call as the Newton-Raphson's method. So if you have seen how gradient descent is derived, then you would know the update rule, and the entire philosophy of gradient descent is just the first order Taylor series expansion. And what Newton-Raphson's method does, it takes it one step further. So it's a second order Taylor series expansion approximation, second order Taylor series approximation of a function. And you can see I've written it here explicitly. So that's the second order Taylor series. So this is the second order Taylor series expansion up to the second order, and then we say that it's approximately this. So now you take the gradient of this, you get this. I will not go through how you are getting this, but then one just need to do it in the paper, and then they will see that this is what you get. Now you say let x start with the minimizer of f of x, then the gradient of f of x star is 0. You can plug it back here and see that you get this. Okay, now you have to recognize this is the Hessian of f evaluated at x, that the kth x, and this is the gradient of f evaluated at xk, or the kth x that you will get. Okay, for the ease of writing, I'll just denote the Hessian evaluated at xk as hk and the gradient evaluated at xk as gk. And so how does the algorithm works? Well, it's quite similar to the gradient descent. Please listen that I have used the word descent, and I'm doing it for convex. So you will initialize some x0. This is a controversial statement, and I'll come to this a little later. You will set something what we call as a tolerance. So you never actually, so most of the time you never converge to 0, but then you can set up something like 10 in the order of 10 to the power, in the order of like -8. So 10 to the power -8, 10 to the power -10. And then if you say that you're within that tolerance, then you have actually converged the optima. So until you are reaching there, you keep on going, and what you do at each step, you go in the opposite direction of gk, that's the gradient. So if you just remove this, then it's just the gradient descent algorithm, but then this hk inverse also helps you. That's the point of the Newton-Raphson's method. So why do we do it? Well, what we in numerical analysis, you will, if you have heard about it, Newton-Raphson's method enjoys what we call as an order 2 convergence. So like putting it very informally, it enjoys a very quicker convergence. So something around like if gradient descent takes about 100, then it should do it within 8 steps. So that's a lot increase in efficiency. So that's why we propose the Newton-Raphson's method. But then this can be only done if it is twice differentiable, and then why we require that is quite clear, because we need the Hessian. If the function is not twice differentiable, the Hessian might not exist or be ill-conditioned, and then can hamper. So gradient descent works with just one differential. If it's differentiable, then gradient descent works, but then for Newton-Raphson's, we need at least twice differentiable. So, but then coming back to the original problem, or logistic regression problem, you can recall that I have proven that LW is negative, what we call LW is concave or linear in some direction. So I have to actually modify this a little bit. So in place of convex, I'm dealing with something similar to a concave function. So instead of going opposite to gradient, we will go in the direction of the gradient. That's why we replace the minus with a plus here. And you can see what the G and H will be. Now, there are some things that need to be said. Unlike gradient descent, where the initial choice of W, or yeah, at least here, the initial choice of W was free. You could choose any point as your initial point. It's not the same for the Newton's Raphson's. Mathematically, there exists a ball. Well, I'm not really clear if it's a ball or a sphere. There's a slight difference, but for our sake, we'll just stick to a ball. So there is a ball around the optima. That's the W star, where you want to converge, of radius lambda, and you have to choose your W0. This 0 will be on the top. There's a slight mistake here. The W0 within that ball, so that it actually converges. Otherwise, it can diverge. Why, I will not prove here, but then there's a constraint on the initial condition, unlike gradient descent. So how do we deal with it? One beggar's way is to actually do this thing where you apply gradient descent for a few steps, and then whatever you are getting as the final W from there, set that as the W0 for the Newton-Raphson's method, and converge the rest of the path much quickly. But then this is a very bad way. There are other specialized and superior way of doing it. So people, if interested, should check out what we call as a quasi-Newton method, a damped Newton method, or there are some other regularized versions. People can check that out. One good source will be IIT Kanpur has started an optimization algorithms course on NPTEL. You can go to IIT Kanpur NOC, and there you will find it. This will end, the lecture is going on, but then you can see that the professor discusses these there. He also actually proves that Newton-Raphson's has order 2 convergence, while gradient descent has order 1 convergence. And then he actually proves that why this is necessary. Okay. Now, one more thing, that you see that there is a matrix inversion. And if you have been doing MLT, then you would have probably heard that the inverting a matrix would take an order of n cube time, where n cross n is the size of the matrix. So that's quite computationally expensive, but then, it's a double-edged sword. Forgive my pronunciation, but then it's a double-edged sword. Like, you have to see that the number of steps that gradient descent is taking, my Newton-Raphson's take quite less, but then do you have the enough computation power to spare that at each of the step you can invert a matrix? If you can, then it's better, but if you can't, then you have to stick to gradient based approaches. Okay, one more thing that I missed, the stochastic gradient descent while I was discussing. Well, this indeed converges to the W that you get from gradient ascent in high probability, but then the convergence can be quite bumpy. So what you do is called a mini batch gradient descent. In that, instead of picking one single point, you pick a batch of points, and then the convergence is quite smooth. So that's one thing that one should keep in mind. Okay. Now I will talk about what happens if the likelihood function is linear, or what happens if my likelihood becomes 0. So why? What happens if my L of W becomes 0? Well, it is at least $1,000 question, if not $1 million. Why? Let me just. Okay, so I will have to just snip it out. Okay, I'm explaining here. Yeah. 1 second. Sorry for. Wait. What's happening? Why isn't it increasing? Okay, so okay, my hw of xi is a value that belongs between 1 and then, if you know, and there is a log before that. So if you know that it's my log function is something like this. So I'm probably sure you know is 0. Fine. So this is how your log behaves. So log is negative between 0 and 1. So when you are maximizing L of W, you are actually somewhere negative. So even this is negative. Please keep in mind, even this guy is negative, because HW of Xi is between 0 and 1, then 1 minus HW of Xi also belongs to 0 and 1. So even this is negative. So these are all negative terms, and you're summing up negative terms. So what happens is, when you're increasing the likelihood, it increases, but then these are negative points. So my L of W increases to 0 maximum. Why to 0? Well, what's the best that can happen? My W in HW of Xi is giving me either 1 or 0. That's the best you can hope for. It precisely predicts if the label is 1 or 0. That's what we are looking for. So what happens if it starts precisely predicting? So there exists a precise W for which we can, predict my Xi's accurately, like dead accurately. So what happens is, these start predicting either 0 or 1, and then this becomes 0, my L of W. But then there's an issue with this. So the question is why? So we are trying to find the best W. If it exists, then why do we even care if it's making our L of W 0? So here's the issue. If it is making, so if my HW of Xi is predicting 1 or 0 precisely, then what is happening? Well, for that you would have to recall a little bit of limits. My H of W of Xi is 1 if this thing actually approaches infinity, and it's 0 if this thing actually approaches negative infinity. Okay, I think that's not clear. So what happens if this is true? So this approaches 0. Not equality, there's an approaches here, to be very precise. Okay, this is 1 by infinity. Okay, fine. So the W is increasing unboundedly, and then that's a challenge. Why? Because my MLE won't exist. At least in finite terms, it won't exist. And this was an important point of the presentation. And then how do I address this issue? Well, there are regularization techniques. There are other two approaches we will not discuss, but then I want to discuss this one, and then I'll provide an L2 regularization method. Okay, so, well, Firth actually proposed his regularization term. So regularization, what do I mean by regularization? It will regularize my optimization problem, so my W does not increase or decrease unboundedly. Okay, so, well, Firth, when proposed it, he proposed it to remove what we call as a first order bias in MLE. Now, if you would recall, I said my MLE is an unbiased estimator. 1 second, guys. Okay, so, well, Firth proposed his regularization term to remove what we call as a first order bias. And unfortunately, I will not be able to show how he removes it, but then I will show that the regularization term actually works. So what's the regularization term? Well, for that, you would need to know what we call the Fisher information matrix. I have provided it here, but then it would take me a lot of time to actually explain why this is a good choice and then what happens. But then you should know I of W is a Fisher information matrix, and what it does is that it quantifies the amount of information that the sample contains. So it's actually a good parameter to estimate how much information is there in the sample. And then what Firth proposed was, you should recall that this was a log likelihood function, and then he said that let's add this term. And this is a new log likelihood function that we want to put in our optimization problem. So which was our optimization problem? This was our optimization problem. So in place of this one, what we will do is this. Okay. So now I would skip some steps. This is not mod, this is a determinant of the matrix. It's not mod. So log takes single value. So log of x, my x is an r, so it's a determinant of I of W and not mod. Okay, now what's the corresponding score function? Well, the score function is nothing but the gradient of L of W that we set in our MLE. This is what we refer as the score function. So for L of W, it's E of W, and then we will, since my L has become L star, the U of W has actually changed a little bit, and this is what we have. Now, this to show this requires a little bit of effort, but then I hope you can find it out in the internet. Or actually ask ChatGPT, but I don't think ChatGPT gives quite a good answer in differentiating this. But I won't go into the how you get this after differentiating this term. So this must be like visible. I'm differentiating L of W and getting U of W. So U of W is nothing but the grad of L of W. And then differentiating this, you would get this. And as usual, my MLE, so my MLE satisfied this equation, and the estimate, the modified estimate will satisfy the U star of W hat equal to 0. And then the optimization problem is laid out here. This is what we are referring as a regularization term. Then what I want to show is that this regularization term actually works. Like it actually stops W, like it actually it penalizes W to reach infinity. It works against it. So my W transpose Xi approaches infinity, then this approaches 1, and then this term approaches 0, this term approaches minus infinity, this term approaches 0, so the product approaches also 0. And then if you recall how the I of W, so if you recall the matrix, Hessian matrix, and well, I of W is nothing but the Hessian matrix, at least for the logistic regression case. So please recall that it's just the negative of the Hessian. This was the Hessian, and then it's the negative of the Hessian, and then you should recall in the Hessian we had this term. So no, so this one. Okay, so what happens is that each of the terms start approaching 0, and then my matrix approaches 0. Well, this is not a very good way to write it, but then again the advice remains same. Just do it explicitly for a 2 by 2 matrix, and then see that my matrix is approaching 0, and then the determinant of a 0 matrix is 0. So my determinant also approaches 0. So the log of the determinant approaches negative infinity. So if my W increases unboundedly, the optimization problem decreases unboundedly. So it is penalizing my W to not grow unboundedly. So that's what I've written here. We have seen that the determinant of the Fisher information matrix vanishes as W approaches infinity, forcing its algorithm to diverge negatively. And then this actually penalizes back the optimization problem. So my W does not diverge to infinity. Okay, the same formulation, this optimization problem can be received by what we call as a Jeffreys prior. So we say that my W, the probability of W comes from this distribution, the square root of the determinant of the Fisher information matrix, but we won't go into this. But then one can check out that how this is quite equivalent to what we have described here. Well, we haven't described here. What I've just told you here is that this is a good regularization term. and I have not actually said what this does is actually it removes what we call as a first order bias in MLE, and even that I have not shown how it does that, but then one can check that out. Okay, so how do we, so once I have the optimization problem, what we can do is we can do the Newton-Raphson's method again. I have provided it here, one can check it out. Okay, so there has been a little bit inconsistency from me. So when I have written here W, I am telling that the gradient is taken with respect to W, which I've omitted here in other places, but then please just see that. One thing that in actual computation, we simplify it a little bit, but I won't get into that. But then this actually simplifies a little bit, because you see there are too many inversions happening, and that's not quite a good way to do. There are simplifications, but I won't get into that. And then I will show you what we have, the L2 regularization, and that comes if you assume that the W comes from a Gaussian prior with mean 0 and have a unit variance, but then it's a multinomial distribution. So it's a multivariable normal distribution. Or okay, so that is not the correct term. It's a normal distribution in not in just one dimension. So that's
Just a multivariate is one.
Multivariate, correct. Sorry, yeah, fine. And then that's the probability form. You have to just see how the normal distribution changes a little bit, the formulation, but then it's the same. And then what we do is called a map estimation. That's the maximum a priori estimation, which was also covered in statistics too, if I'm not wrong. But then if not, you can just see what I've done. Like, this is a very straight cut way of estimating. And then you get this kind of a turn. And then this is what we call as a L2 regularization. And then you can match the coefficients here. And then you can see that my sigma is nothing but 1 by sigma square. So that's one. So even this also does the same. It prevents W from diverging. So those are two regularization methods I promised I will show. Now is the interesting part. Why? If you recall, why did we choose this? So why did we choose this function, HW of xi, as the probability that y equal to 1 given x? Okay. So, and I said that it's just not enough to say that this function is between 0 and 1. Then what's enough? Well, if you recall that at the very beginning, I said my logistic regression was a classification problem. And then for a binary classification, what we can say is that y given x follows what we call as a Bernoulli distribution with some parameter p. And then one good argument is, why don't we just estimate p from the data that we have? Well, that's one way to do it. And in fact, we have done that very thing, but instead of Bernoulli p, what we do is we derive a functional form and then predict the parameters of that function. So the functional form is precisely this. And then we start like estimating this W in place of just this one numerical value. This gives us a lot more flexibility. One like small thing that I will show, one of the way to get this, but the way I will show is not the only way. And that's why it makes it more general. It's just not, we are deriving from Bernoulli, but then there are multiple other ways from where you can come to this exact form. I will name a few of them, but then we have to cover some background materials and I have to be quick. So what we call a sufficient statistics, for a parameter of the sufficient statistics is something that when you have that, you can throw away the parameter, like, or the estimation of the parameter from the data. A very simple example, and I won't go through the definition, one should read it out. I've provided the PDF, is that if you have that the coin toss follows some Bernoulli 1/3, do you really, and you have estimated this 1/3, do you really need the data set to say that how many heads you will get in one turn? Well, no, you have this. And well, that's what we essentially call as a sufficient statistics. It is not that simple, but then yeah, that will suffice. And then exponential family of distribution. So this will be covered in week 12 of MLF, if I'm not wrong. But then this is one thing I want to show you how. So if we start with some probability distribution and then we want to generate a family of that, how do we do that? we do something called an exponential tilting. I will come to these names because once I've derived this form, these names will make much more sense. So what we do is we start with a probability distribution which follows some kind of distribution D. And then I will generate a family of this distribution D. So how do I do that? Well, the probability, so this is a random variable. So probability that x of x equal to x. But then that was also same. So what we will do is we will say, so this parameter eta is what generates the exponential family. It's proportional to something. So it's b dash, and please just I'm using the notation quite meaningfully. It's not that I've missed a b dash here. They're different, and I will show you how they're different. B dash of x times e to the power eta x, and then from this we'll actually generate the distribution. This process is what we call as the exponential tilting. This is what we call as an exponential tilting. Why do we choose to generate the probabilities by multiplying this? Well, there are much statistical theories that I won't go into, but one very interesting thing about e to the power x is that it does not create discontinuity or issues with differentiability at points where the original function was actually differentiable. So it can never happen that my initial function f was differentiable at some point a, and adding, so this function will also be differentiable at that a. But then that's not one, that's a beggar's reason. Okay, but then there are statistical theories that have been developed, and well, that's just not the point of the discussion today. So what we do is, you see that I'm just using the proportionality symbol because, well, this can be that this might not be an actual probability mass or probability density function. So what we have to do is normalize it. How do we normalize it? Well, we just integrate it. Okay, this is small x, and the capital X I will write it a little differently. So don't think this is the chi. So this is generally chi, but then my handwriting is not that good. So the capital or a small letter might not be quite distinguishable. But then there's the support. And what we have is, you should recall from statistics too, that if you had something like this was nothing but the expectation of g of x. This is from statistics too. If I'm misreferring something, if I'm telling that it is present there and it is not, and if you know it, please just tell me, okay? Like if I'm misreferring to things. But then, yeah, if I recall correctly, then this is from statistics too. Okay, so why this? Well, a quick example is, if you have two numbers 2 and 5, how do you bring it between 0 and 1? Well, you divide this by the sum. So this actually integration like can switch. If you're dealing with something like a probability mass function, then it can switch to sigma, but then you won't be ever dealing with a probability mass function because it's a continuous function. So we'll always be dealing with some density. So in place of a summation, you have an integral. Okay, so what we have is the probability equal to b dash of x e to the power eta x, this is eta, by what we have is the expectation of e to the power eta x. So what happens is, then you take it into log. Okay, now this. So what can happen is, this can have some terms that depend on x, These are all capital X, by the way, which can depend on x, and then you would accommodate all of them in this b of x, and you will just take, you are taking exponents, so you will have a log there. So a of eta is purely a function of eta and not of x. That has to be kept in mind. Okay, so this is how you actually get this form. One small thing, you have a t of x in place of an x. Well, in some distribution, t of x simplifies to x, but then I have done the very same thing for t of x, the sufficient statistics. sufficient statistics, you get the same thing, but then you are dealing with like you're dealing with vectors, so you have to be very careful. Like it's not necessary that this eta and this t of x are like both of same dimension. If they're not in same dimension, you can't really take a dot product. But then what you do, well, you have to like consider some bilinear forms. Like you have to consider n transpose mt of x, where m is a matrix that you form with different constraints, but we will not be looking at such examples today at least. So these names, well, x is the observed data, n is the natural parameter, or this is the parameter that generates the family. You have this log partition function. Why partition? You can also say log normalization function, or I have seen cumulant function, so which ensures actually the normalization. So what happens is that this term is so this normalization is called partitioning in statistical physics, and then you take a log, so that's where this log partition name comes from. B of x is called the base measure, but then you can like debate, like B of x was not really so it was not the base probability from which the family was originated, but then B of x is named the base measure. I don't really have some explanation why it is named that, but then you understand that B of x has components which actually help you generate this family. Okay, nice. So that was a quick recap of exponential family of distribution. This T of x is a sufficient statistics which I've already defined, and then we are at the very last, and then I'm ready to actually tell you how this form comes. So now, okay, so if I will generate what we call as the exponential family of the Bernoulli distribution. So if my y follows a Bernoulli phi, then P of y can be written as phi to the power y 1 minus phi to the power 1 minus y. I have actually talked about this, how this is just the compact way of writing it. And then I'm just taking the exponents. There is nothing. So I'm doing exponents and logs, so this should cancel out. What I'm trying to do, so okay, when we call something as a family of exponential distribution, so if we can match it to this very form. So that's what I'm trying to do here. So you can see I have done that. And if you see, I have this. And then you can actually, match the coefficients. So I will actually do that. So what you have is exponents log of phi over 1 minus phi times y plus log of 1 minus phi. And then what you had there was B of x exponent. What we had was, so you had it in x and I'm having it in y. So just forgive me for that notation error. Exponent you have, okay, y times t of y, and then you would have what we call as the a of eta. So you can actually match the terms. So what you have is t of y equal to y for Bernoulli. T of y equal to y is what you have for Bernoulli, and then you can actually compare. So wait, what? Okay, sorry, this is not y, this is eta. Okay, that's eta. And then you can actually compare that eta is this. Well, then you can actually write phi as 1 by 1 plus e to the power minus eta. It's not done there, but you can see the form is coming. So, and then I will actually show you. So then we have to discuss again some background. I will not go into this, but then this is a way. So you have some kind of probability, then you want to convert it into a model. There is something called a linear models, and then there is something called a generalized linear models. Linear models works only for normals, and yeah, I'm not really sure, but it works for normals. But then generalized linear models works for all of the distributions. So you can now, yeah, this is a good time to say that the linear models did not work for what we call as the discrete distributions. But then the moment we have multiplied this e to the power eta x, it's not really a discrete distribution, it's a continuous distribution. So then if the output of y given x parameterized by some theta is exponential family generated by eta, then the hypothesis function that you should model is the expectation t of y given x parameterized by theta. And the eta, this is a strong assumption of the generalized linear models. This is the place where the linear word comes from, this theta transpose x. If you write it down, it's like theta naught plus theta 1 x1, x1 is the first coordinate of x, and so on. That's the linear part. That's how you get the word linear. And then theta is a term that needs to be estimated. It's an unknown parameter that needs to be estimated. Why this assumption? Well, you can see that if you have a data set, predicting the mean is quite a good way, and then you can actually kind of build an intuition why this expectation is taken. But then this is a model, this is the enforcement, this is an assumption that you make, and then we are finally ready to do it. So recall, so now recall the logistic regression. I said that this was a good choice. This is actually a good thing to do. Well, I will show you that I have done exactly that. So my y given x is a Bernoulli phi. Then the h theta of x, the hypothesis function should be this. Recall I have already proven that the t of y for Bernoulli is just y. And then you recall that expectation of y given x. So expectation of a Bernoulli is the expectation of Bernoulli p is just p. So expectation of Bernoulli phi, y given x is Bernoulli. So expectation of Bernoulli phi is just phi. And then you recall again, I have shown that phi is of the form 1 by 1 plus e to the power minus eta. And then recall, this is a fact that we enforce while applying generalized linear models, is you replace eta with theta transpose x. And if you just recall, you had this very form when you had a w there in place of theta, and you're estimating theta. So recall that theta was a parameter that needs to be estimated, and you have explicitly done that. So you have finally found why the sigmoid function arises naturally from the choice of Bernoulli distribution. So if someone questioned that why didn't we do this, well, the answer is we did this, but with a lot more flexibility. In place of just estimating p, which would be a single value, you create a functional form, and then you estimate the parameters of the function. Okay. If you know Gaussian discriminant analysis and naive Bayes assumption, then you can show that when you have a binary classification problem, and if there is the variance of each of the class is equal, then you can actually, from the proof of the decision boundary, like if you just exactly prove out the decision boundary is linear, the exact proof can be, you replicate the exact proof, and then you will get that you are getting this form. So well, that is one reason that you say there was a comment that logistic regression asymptotically is very similar to what we call as a Gaussian discriminant analysis. So asymptotically, both of them do the same thing, but it's seen that logistic regression performs like much better. Okay. Well, that was all that I had today. I will provide you with some links that I want to share. So these links I have provided, these are all clickable links, like you can click them, you will get there. But then these are some materials, the CS229, but then I like, okay, this removes me from here. Okay. So where I was here. These two are like introductory material, like you can do them parallelly with your MLT course if you have time. And if you are like not satisfied, which someone who is learning shouldn't really be, then you should actually go into this. This is quite like, it's not advanced, it uses the same thing, but then you would have to be like actually eager to learn new mathematical tools. So I would mention that if someone has doubt why the kernelization trick works, then you can actually see this course, and then you can see the lecture for what we call as a reproducing kernelized Hilbert spaces. But then you would need a little bit of understanding of what Hilbert spaces itself are. But then you can actually see how the Mercer's theorem works, which was introduced in the the second week of MLT. The professor gave you an informal version, or what he gave you was not an informal, but it was a linear algebra. So when your vector space is finite dimensional, the theorem he gave is actually correct, is precisely correct. But then if you have an infinite dimensional vector space, then you have to actually, then the Mercer theorem changes. So the summation goes to integration. If you recall, he mentioned there like estimating functions to as points in limits. But then you can actually see them here. One thing, both of them provide a different view of machine learning, as you can see, but then they are both provided by the University of Tübingen. Sorry for my pronunciation. You can actually click this. CS229, I would say you should follow their book. That's quite nice. Cornell lecture series is also quite nice, but then these two like go into deep stuff. These are let me just be clear. These are all graduate level material. These are undergrad, but then this is a graduate level material. So the rigor is slightly more. You can actually see this one. It actually explains the probability and probability measure and those words quite nicely. So one who is interested in probability can watch first two lectures of this. Well, that actually covers everything I have provided. Yeah. Okay. That was from my side. Please, if anyone has any question, feel free to ask me.
Okay, I think that was quite deep, Swarnabu. Didn't have this PDF to begin with, so I was not actually able to,
Yeah.
take up the whole thing in one go. It'll take some time, maybe.
Yeah, this actually took time for me to actually encompass the material. But then what I want to emphasize is that the mathematics is actually boring here. It's you are just taking derivatives, and well, that just takes practice. There is nothing deep to it. You can
Yeah,
see that
that's
there
right.
are multiple
It's
times you
more
have this.
mechanized kind of thing, but then the trouble is the entire machine learning is almost like the same thing, right? It's just a
Yeah.
bit of. Anyway,
Well,
there
not
was
that.
one little thing, by the way, that I wanted to actually ask.
Okay.
I mean, it was way back in the earlier thing. You said regarding the gradient descent and the stochastic gradient descent,
Yes.
right?
Yes.
So in
Well,
the
ascent, not descent. It was
okay
ascent.
ascent, yeah, but yeah, this SG, the stochastic one,
Yeah.
uh, we argued that it actually, if the number of data points are too large, for example,
Yes.
and then the computation becomes too much.
For the gradient ascent.
Exactly, for the gradient, then you should possibly go to the stochastic one, because
Yes.
that might be less computational intensive.
You don't have the summation.
Yeah, but then don't you think it's going to be taking a bit longer? So whatever gain in the way of less computation is actually going to take more number of computation in the sense of longer ones.
Okay. Here's a good point. So if you recall, I said it's a double-edged sword in case of Newton-Raphson's method.
That was Newton-Raphson. Yeah, that's correct.
I said that you had to invert matrix, but then I said if you have the computation power, that you can spare it for inverting the matrix. So it's like it depends. Like if the matrix, I argued that if the matrix was too large, the computation of the inversion would actually hamper, the improvement it provides.
Yep.
But then it can happen that, so like I argued, if the gradient descent takes 1,000 steps, the Newton-Raphson's method does it in probably 20 steps. But then you have to actually see that how the number of steps is reducing, correct? But then what's the overall time that's taking?
Yeah.
Not just the asymptotic complexity, but then what's the sample time it is taking. And then that's a double-edged sword. Similarly, it's a double-edged sword for the stochastic gradient descent. And then I actually later on, I missed that part. And then I said that in place of taking single points, you should take a batch of
Yeah,
points.
you can take the batch.
Batch batch gradient descent or whatever that is called.
Mini gradient. Yeah, that's
Yeah.
mini batch basically.
Yeah, but then that's same. Instead of picking single point, you can pick a batch of points and do the computation there.
Right, that's correct. That's correct.
Well, one thing, like if you what I missed today, which I want to talk about, is there is a very nice theory. So actually, when I was telling, I said that Fart was not looking in, at least he was not looking at this machine learning perspective. What he was trying to do, so he was trying to reduce what we call as the first order MLE bias.
Yeah, that's correct.
So what that is, well, MLE, I said that it's asymptotically unbiased, which is a bold claim, which needs some kind of proof. I don't know if I didn't have time, but then later on I can maybe present. I have a material on that.
Yeah.
But then in sample sizes, it's biased. So
A small sample size will be usually biased.
is biased. So what he tried to do was to remove that bias, and then he later on realized that removing the bias, the formulation actually regularizes the optimization problem too.
Right. Okay.
Well, and I propose that the regularization of it was like you can come from what we call as Jeffrey's prior, but I didn't go into that. And then because that was a very similar way of doing that map estimate. So in map, you assume a Gaussian prior for W. And why you assume that the mean is 0? Well, the argument is that if my W is very close to 0, then the separation is more simple. Like it's simpler. Like it's very vague argument, but then that's the argument at least I know as of yet. It's a very good question that even I am like trying to find out. But then it's very similar. So the Jeffreys prior and the L2 map, the L2 regularization. From L2 regularization, you get that minus lambda by 2 mod W square as the regularization term. From Jeffreys prior, you would get this Furt's penalized regularization term. And they are just equivalent. You can prove that they are equivalent formulations.
Fine, that will be that's a good. Anybody else has something to ask, by the way? Anushka, you have to say something?
No, it's fine. It's fine. Actually, it was really very deep and very insightful. With full of mathematics, so it will take me some time to invite the whole thing after hearing the lecture. I have to see the notes as well because I myself forgot a lot of things. So it will take me.
Like I should have said that this was more of a literature review than a presentation.
Yeah, it was
I
most.
tried to.
But it actually tries. You introduce quite a lot of things
Yeah.
which many people won't be familiar with actually. So that's a good way. At least it gives us a way to explore the things over there, right?
Yeah,
At
the
least the
points
initial point.
that I said can be explored quite more deeply. Jeffrey's prior is one example. I proposed multiple improvements. So the quasi-Newton and damped Newton methods. So I proposed a very beggar's way. So apply gradient descent for some step and then Newtons. But then you can see the issue with that because it can happen that even after many gradient steps, you don't get within that ball.
That's definitely correct.
So you have to do those. But then, yeah, I think that I have covered all the topics that one should explore in this. I don't, yeah, I have probably covered.
Yeah, you have covered more than what is required actually. I must say, basically it will be taking some time for people to absorb the whole thing actually.
Yeah, it had too many prerequisites. I was referring. Okay, one thing for the people who are left, which I missed, please. I found this that IITM. If you go to the BS portal, they have actually uploaded statistical computing, the lecture series of MAM. Please watch that.
Okay.
If anyone is listening, please watch that. You can see the estimation maximization algorithm, which is explained quite good. Ma'am actually explains Newton-Raphson's method better than me, of course, like no comparison. She also, you can watch that. That's a very good, you should do that in parallel to MLT, or at least mark out the things and you can actually see many of them are covered in statistical computing.
Okay, fine.
Okay,
So
yeah,
I think
that one can check out the BS portal.
yeah,
They have
sure,
actually
Swarnava.
uploaded the entire lecture.
Okay, fine. Thank you, then, Swarnava. I think that was quite a informative session, right?
Yeah.
So Shubham sir has joined. So
actually, me and Shubham sir actually discussed my paper, and then he suggested some things that I should eliminate.
yeah, actually, I couldn't get hold of this PDF earlier. Actually, I just saw this today in the.
Actually, I had to remove many materials.
One today only. I don't think I saw this paper from you.
Yeah,
This was actually given later on the pi square G space actually.
So what happened is actually I had to remove that proving that remover